I don't need to spend too much time to do that. You know, he's a star, I would say, you know, a rock star at the University of Delaware. I couldn't say he's one of the reasons I came here, but even before I came here, one of my common friends right now is a professor at Purdue University. He said, "Oh, you're gonna join, you know, Delaware. I should definitely visit you because I have another friend, Andreas, is working with us, and that's the first person I got to know here. But unfortunately, I'm so glad that we arranged this talk. And some of you probably heard about that. He will be moving to Cornell University. So this will be you shake hands just now, that will be maybe the last time you will see he give a talk here in one of the Delaware campus. On one side, congratulations to him, you know, to moving to Cornell. Other hand, it's a big loss to the University of Delaware. Particularly, I saw when he was at Oak Ridge, he leads the sustainable mobility. That was exactly when we come here, what do we want to do, right? Yeah. We will. Yeah, I think it's a kind of you know, mixed feeling here, but we're so glad that have you know, Andrew coming here and share with us with his, you know, cool research. So without further ado, and
thank you, Hayes. I appreciate the invitation and the kind words. Good afternoon, everyone. Thank you for coming on a nice Friday afternoon. I will try to keep it entertained. I know it's Friday, it's the end of the week. Let me remove this. Okay. So what I plan to do today is to walk you through some of my past research that I have used learning and model-based control, and try to make the case that by combining model and learning, model-based control and learning, might be more advantageous for applications related to cyber-physical systems, and in particular to emerging mobility systems. So the world is changing, and one particular sector that undergoes significant transformation is transportation. We're about to depart from typical conventional vehicles with internal combustion engines and move on to electric vehicles with electric motors and batteries. And this transformation provides several challenges and opportunities. For example, we need to update our current infrastructure with charging stations. We need to coordinate the increasing demand of electricity to charge the electric vehicles. We have the opportunity to integrate the electric vehicles with commercial and residential buildings, so that we can make up off-grid buildings that will not require electricity. At the same time, with the introduction of connectivity and automation, we can use the shared information across the vehicles and coordinate the vehicles in specific scenarios like intersection, emergency roadways, speed reduction zone, and then improve transportation efficiency and also travel time. Now, as you can perhaps observe here, is that all these applications, they have a common theme. There is a cyber component that or information that we can use in order to control the physical entities, the vehicles. So it's essentially we're dealing with cyber physical systems. Now, somebody might ask, why should we be focusing so much on transportation? Well, in 2017, the US consumed on average 19.96 million barrels of petroleum, and transportation accounted for 71% of that usage. This is enough to fill up the Empire State Buildings over 2 times per day, just to propel vehicles. So you can see the impact of transportation in energy and how we can address this, creating a more sustainable environment. Hopefully, with the introduction of connected automated vehicles, we have the opportunities to coordinate vehicles and improve efficiency, transportation efficiency, improve travel time, and come up with a more sustainable mobility system. So what I plan to do today is to go over some, automotive/mobility related applications that I've worked in the past using learning techniques and also model-based control techniques. And then I will try to highlight some of the challenges that I encountered and some of the cons. And then at the end, I will have a few slides just to briefly touch about how we can potentially combine learning and control and address these challenges. Before I get to the technical talk, let me acknowledge the contributions of my students. Some of them are here and some of them are online, I guess. In the IDS lab, we develop frameworks and algorithms that can make cyber-physical systems able to realize the optimal operation while they're interacting with the environment. And in particular, we're focusing on applications related to smart cities, mobility, socio-technical systems, and so forth and so on. To validate some of the concepts that we're working on, we have developed a scaled smart city, 20 by 20 feet or 6 by 6 meters, in which we have robotic cars on a scale of 1 to 25. And we use this scale testbed to sort of prove concepts related to transportation. How we can coordinate vehicles, how we can, first develop first last mile kind of, approaches. So this is a particular scenario that we use, drones to collect some information from the vehicles and use this information to do some better controls. We have also integrated driver emulators in our cars, so we can drive the cars inside the city, and we can perhaps have a so-called mixed traffic environment when you have human-driven vehicles with connected automated vehicles. We have located some sensors ahead, in cameras ahead of the cars, so the driver can drive the vehicle, and through the camera, they can see what's going on for the car. So this is a nice testbed to sort of, do some of that testing. We have also, several drones. We have several drones that can coordinate with the ground vehicles, and we can explore other type of applications. So when we have collaboration and cooperation between ground vehicles and drones. We have also built up a digital twin of this testbed during the pandemic when we didn't have access to the city. So my students built up this environment where we can share. If this is in Sumo, they can share, and somebody can develop their approaches. And once this becomes mature, they can do physical experiment in our scale city. We have also built an app using students from computer science department and from the senior design. And they have built this app that we can use to sort of, mimic a shared mobility type of approach in our scale city. So we can call a car, the car will come to artificial origin, and we can assign an artificial destination. So that's the kind of approach that can, validate some of the eco-routing work that we do in the lab. The city was featured in one of the last issues of hybrid control systems last December as a front cover. We also have a driver simulation testbed with 6 driver simulators that we can use commercial software like Prescan, VSync, Carla, and others, and do some of the work. So essentially, this is the starting point in the lab. This is where we start. And once we prove concepts, then we move to the scale environment. So with that, let me get back to the technical work. So I've been working over the last several years in different aspects of transportation. I started with my dissertation on how we can make internal combustion engines able to learn the optimal operation with respect to the driver's driving style. Then I moved on and started working on power management control for hybrid electric vehicles and plug-in and hybrid electric vehicles. And over the last 12 years or so, I've been working on connected automated vehicles and how we can use the shared information and do better control and improve transportation efficiency and travel time. So what I'm going to do today is I'll walk you through my journey, starting from my dissertation, and try to highlight some of the challenges across these boards, and then give you some insights about how we can address these challenges. So my journey started in 2003 when I landed at Detroit to start my graduate studies in Michigan. It was about 11 inches snow. So the first thing that I had to do is to buy long shacks in Michigan and settle in for the winter, for the weather. The second thing that I had to do is to find the challenging.
No, from Michigan.
Yeah. The second thing that I had to do is to find an interesting problem to dig and identify for my dissertation. So I was reading several articles and journals to identify an interesting problem. And I came across a common question at that time. Why you cannot achieve the miles per gallon posted on the window sticker of our cars? So everybody was complaining why they cannot achieve the fuel economy that they're supposed to get with their car. So I thought that this is going to be a very interesting problem. So I started working on that. To understand fuel economy in vehicles, we need to look at the engine operation. So when we buy a vehicle, it comes with a window sticker, and this window sticker indicates the fuel economy for city driving and fuel economy for highway driving. Now, although we can always get the fuel economy for the highway driving, we can barely get these fuel economy estimates for city driving. So let's see why is this the case. Now, to understand engine operation, we need to look at the brake-specific fuel consumption map, which is this colorful contours, BSFC contours, brake-specific fuel consumption map, which gives you fuel consumption per unit power. So the lower the value, the better, because the lower the fuel you consume, the more the power you get. And this BSFC map is given with respect to engine torque and engine speed. I'm sorry, the fonts are a little bit small for this, but hopefully you can see. Now, as we accelerate, this is the speed profile of the vehicle. As we accelerate the vehicle, the engine operating point jumps from point to point on the BSFC map. And depending on where located, we have the corresponding fuel consumption. Now, the question is how we design these colorful contours. Now, the way that these are designed, the BSFC map is designed from the OEMs, they take the engine operating domain, engine torque and speed, and discretize it to a finite, usually small number of steady state operating points. Steady state operating points means that we operate the engine at constant torque and constant speed. And then as they operate the engine at steady state operating points, they fine tune the different variables of the engine, control ejection timing, spark timing, VGT, EGR, whatever they are available. And then they take this map, they put it in the electronic control unit of the engine, and as we drive the vehicle, we interpolate the values corresponding to the steady state operating points, and this is how we can control engine operation. However, while I was at Michigan, some colleagues of mine who used to do experimental work did the following experiment. They operate the engine at a constant operating point, and they notice that the fuel consumption is constant, what we expect. But then they notice that if we approach this operating point from a sequence of operating points, then fuel consumption varies for a small transient period. And moreover, if we approach this operating point from a different direction, fuel consumption is associated with different values. So what happens when we drive the vehicle in the city, we operate the engine under this operating transit period. And so the steady state operating points do not really give us the optimal results. Now, to optimize the engine for every different transient case is infeasible, simply because every driver's life is different. So you can't really identify all the different cases of different drivers. We have an infinite dimensional space of the driving cycles. So what I did in my dissertation was I thought that instead of focusing on steady state operating points, I focused on engine operating point transitions, built characteristic of the driver's driving style. So I modeled the engine operation, the evolution of the engine operating point as a control map of change, and then I developed a controller that can learn the transition probability matrix and transition cost matrix of this model. So eventually, the implicit assumption was that as we learn the transition probability matrix, we eventually learn the driver's driving style. And the more the driver drives the vehicle, the more we get the learning about the transition probability matrix, and we can apply some control to identify the optimal operating the optimal values of the operating points with respect to the driver's driving style. So with this approach, as the driver drives the vehicle, the engine can be optimized with respect to his driver's driving style. If any other member of the family drives the vehicle, the engine can recognize and can adapt accordingly. So, although with this approach we were able to get at least 8% improvements, there are some disadvantages of this approach. For example, when we identify the feasible set to explore the action space, right, this feasible set changes with respect to the environmental conditions. So if you identify the feasible operating point, the feasible action set for ejection time, spark timing, for Detroit, for a vehicle that will operate in Detroit, this feasible set will be different for a vehicle that will operate in Nevada. So we can't really rely entirely on learning the optimal calibration of the vehicle. So that's a standard disadvantage.
So this work is on the ICE traditional.
Yes.
This was when you were PhD at
Yes.
that time.
Yes. So Michigan filed a patent on that. University of Michigan, and I heard last year, a couple of years ago, that they have opened discussions to license this technology to affect John in Silicon Valley who work on it. So the idea is how we can make the engines learn how to optimize their optimal operation. But the disadvantage here is that we can't really rely entirely. You need to have an adaptation scheme, and this is going to be my discussion at the end of the presentation. How you can combine learning with some adaptive control to address this problem. So anyhow, when I moved to after my graduation, I moved to General Motors R&D, and I worked on a similar problem. The idea is how we can learn the fuel injection characteristic curve of a solenoid fuel injector. So they were working on a new combustion technology, and they wanted to have multiple small injections, precise injections. But as you can see, these are 4 different fuel injectors, and they have injector-to-injector variation. So if you command a particular pulse width, you get 4 different fuel injections in your engine. So in the 4-cylinder engine, you have imbalances, which help fuel consumption and also stability and also performance. So the idea is how we can learn precisely the fuel injector curve, so that when we command the pulse width, we know exactly how much fuel we inject. Eventually, this is a typical identification problem. And somebody might say, this is quite trivial. However, the problem here was that I don't have feedback control. I can't really measure. If I command the pulse width, I don't have the measurement inside the cylinder to measure exactly what's the amount of fuel that has been injected. So I use a bunch of combination of what we call today deep learning. At that time, we call it just supervised learning. It was not that fast. Just neural network. So we have a bunch of data from fuel injectors. We trained this data, and then I was starting with some very initial, baseline calibration for the fuel injectors, and then I will start with the fuel injectors. I was able to learn the exact fuel injector characteristic curve. That's the fuel milliseconds in the fuel cycles of the engine. However, what I realized then is that if I change, so I was doing tests in Warren, Michigan, and when I was, traveling to Milford, proving ground facilities, the controller didn't work because I had different temperatures, different environmental conditions. So I had to enhance this approach with some sort of adaptation. So bottom line, I couldn't rely entirely on the offline data that I have to learn the fuel injector curve. I have to enhance my neural network scheme with some sort of adaptation and control. That's another point that I want to make at the end of the presentation. And then we have the 2010 volcano eruption in Iceland, right? And you might wonder how is this related to that, right? Well, at that time, when I was at GM, I was invited at Oak Ridge National Lab to participate in the National Academy of Engineering Frontier Symposium, hosted at Oak Ridge. And they have invited several speakers from Germany to participate. And due to this volcano eruption, all the flights from Europe had canceled to the US. So they were missing speakers. So the organizers asked me to give a substitute talk. And I told them that I won't be able to discuss anything about my work in GM. They told me, discuss whatever you want. So I presented my dissertation. And long story short, I ended up at Oak Ridge National Lab. What was my next station? And then, of course, I moved my research topic from powertrain control to hybrid electric vehicles and plug-in hybrid electric vehicles. So that was, a time step, a step function change in my career and my research domain. So what is a hybrid electric vehicle? Well, with a hybrid electric vehicle, instead of relying entirely on the engine, we have multiple subsystems that we can deliver the power demanded by the driver. So we can have the driver demand for the power, and this can be delivered through the engine, through the motor, or through a combination of that. But all these decisions have to be made in real time as the driver drives the vehicle. So to address this problem, essentially what we want to do is we first identify the physical state action space for each of these subsystems, and then we formulate an optimal control problem that can derive the strategy how to distribute the power demanded by the driver over the long run. So by minimizing the expected long run average cost per unit time. Why we pick up this particular cost criterion? Well, we want to minimize maximize the fuel economy, minimize the losses for long term, as the driver drives the vehicle for days, for weeks, for months, right? We can use other criteria for this particular case. Now, to solve this problem isn't feasible in real time, just because you can only solve a dynamic problem in real time. So what I did in this particular case, I reformulated this problem as a multi-objective optimization problem by maximizing the efficiency of these subsystems. And I eventually came up with a Pareto frontier. So I solved this problem offline for every different realization of the torque demand. And I found the Pareto optimal solution. And then I integrated with a power management controller and integrated as the driver drives the vehicle. And eventually we've shown that we can get the same fuel consumption benefits as we get with dynamic programming. When we use, for the dynamic programming, we use reinforcement learning, tool learning approach. So essentially we have the model of the car and we run it over the same driving cycle again and again and again until we converge to the optimal control strategy. And when we compare it with a dynamic, with a Pareto optimal solution. As a matter of fact, we implement this in our demo vehicle. We have an Audi A3 e-tron operated in Michigan, since we don't have space here. So that was an ARPAI project that we completed a couple of years ago. We led this project in collaboration with University of Michigan, Boston University, Bosch, and Oak Ridge National Lab. So our partner Bosch did the experiments for this case. They ran the power management controller with the Audi's controller, and these are the BSFC maps that I discussed before, right? The brake-specific fuel consumption map, and you can see how the engine operating points are visited all over the place, and in particular in high and low efficient regimes. Although with the Pareto optimal solution, we have squeezed all the operating points to the most efficient regimes, and this is why we get at least a 12% improvement in fuel consumption. Right? We did multiple tests just to validate these results. Actually, our industrial partner Bosch. We actually developed this approach, the Pareto optimal solution, to other applications while I was at Oak Ridge National Lab. So we had a big project where we built a 3D printed a building, and we attached this building with several renewable resources like batteries, photovoltaic panels, and also we attached a hybrid electric car. And the idea is to demonstrate with this project how we can have an off-grid building. How we can have a building that can rely entirely on renewable resources. But in order to do that, you have to have some power management control. So we developed this approach, and we essentially demonstrated how we can use electricity demand, of course, with some specific bounds, and have it entirely being,
This is like E2G.
Yeah, this is
now is
this is everything. So essentially, the car acts as a buffer. You can use energy from the car, or you can charge the car if you have extra energy from the photovoltaic panel all over the battery. So that was a demonstration project. Actually, at Oak Ridge, they built the 3D printed this building. They 3D printed the car. That was all built up at Oak Ridge National Lab. They just bought an engine, and that was all 3D printed car. This is a big demonstration project at Oak Ridge.
3D printed.
Yeah, they wanted to essentially integrate different technologies from BOE, additive manufacturing, systems, energy mobility systems. They want to have a big demo project. So that was several scientists and research staff work on this project. So, and eventually, while I was at Oak Ridge National Lab and working at hybrid electric vehicles, I thought that there is opportunity. At that time, it was 2012, and essentially, when you were talking about connectivity and automation, the people thought about safety only. I thought that there might be some opportunities for energy efficiency. So I submitted a white paper at DOE, which was eventually funded, and I started working on this area, how we can use connectivity and automation to improve the efficiency of the vehicles. And what I have in mind was something like that. How we can use the shared information from the vehicles to avoid congestion. And if you avoid congestion and stop and go driving, you have some benefits directly in fuel consumption. So if you think about it, these are not really new ideas. I mean, the first ever time that they talk about connectivity and automation was in 1939 in the Futurama exhibition, where they had a model for the world, and one subset of this model was about the transportation, and they envision a high efficient transportation system where all the vehicles will cruise with the high speeds and safe. In 1956, GM featured the car of the future, 20 years into the future, 1956. So in 1956, the vision of GM was to build up a fully autonomous car by 1956, which will have all the gentleman that you can see here is what we call today GM on Star, if you drive a GM car. So essentially, the car is fully autonomous. They, show that a family travels from Michigan to Chicago, and they get some information from this gentleman, the GM on Star system as we speak, and from at some point it goes completely, self-driving mode, and they show that the family start enjoying having a very nice trip and so on.
The car looks like it has a tail. Maybe you can fly.
Yeah, there was the Firebird.
The Firebird
too. And actually, at some point, this car passes the Firebird 1, which was a conventional car, and the family makes fun of the other car because this is supposed to be the future car. They have this. I mean, if you have the technical center in GM, yeah, they have that. This car. This is the Firebird 1, and when they get past to this car, they make fun of the. This is the old timer, they say. That's the kind of old fashioned. Anyhow, long story short, over the last several years, we've been working on how we can use connectivity automation to improve the stop-and-go driving, avoid stop-and-go driving in several scenarios. You see, we use the model of MCity since we have the project with Pareto, and we did several testing at MCity. So we have built a pre-scan and VC model, and this is where we use we do all the simulation. So let me give you a little bit of technical flavor how to address these problems. We will consider an intersection, but this approach can be used in any other transportation scenario, like roundabout, merge way, and so forth and so on. So let's consider that we have 4 vehicles approaching the intersection, right? If they keep cruising, they will have a potential lateral collision, a potential conflict. So the area at the center of the intersection, when we can have a potential conflict, we call it merging zone. And then we have the so-called control zone outside the merging zone, inside of which the vehicles can communicate with each other and can exchange information. So the problem here is once the vehicle enters the control zone, to derive the timing that will be entering and exiting the merging zone, and then derive an optimal acceleration in terms of fuel consumption so that they can cross the intersection without stop-and-go driving, without any lateral or real safety concerns, and by minimizing fuel consumption. So if you think about it, what we want to do is that by the time that the vehicle enters the control zone, to derive the times to enter and exit the merging zone, and also the exit of the control zone, and then derive the optimal acceleration with respect to fuel consumption. This is essentially a 2-level problem. In the upper level, we try to identify the timings of the vehicle, so we solve a throughput maximization problem. In the low level, for these times, we derive the optimal acceleration, so we solve an energy minimization problem, right? So in our approach, we model every vehicle as a single double integrator, where P is the position of the vehicle, B is the speed, U is the control input, acceleration, deceleration, and SI is the position of the vehicle I from the distance of the vehicle I from the vehicle K, which is ahead of the vehicle I. Now, somebody might argue here and say, hey, you know what? That's a very simple model to model a vehicle, and that would be a fair argument. What we're trying to do here is to derive an optimal solution in real time. So we need to have simple model dynamics that can give us this flexibility. However, the way that we address these model discrepancies, once we derive the optimal acceleration profile, then we have a PI or PID controller, a low-level controller that can track this optimal trajectory. So eventually, we convert the optimal control problem into a tracking signal problem. And this is how actually OEMs design these controllers. However, this is another point that I want to make at the end. The discrepancy between the model-based control approach, which is what we have today here, and the actual systems control, when we have the actual physical system. I will get to that at the end again. Now, the next step is to define the bounds of the optimal of the control and state of my system. So, for example, for each vehicle, we have a specific acceleration, maximum acceleration, and maximum braking capability. So we need to incorporate that into our modeling framework. And of course, from the time Ti naught that the vehicle enters the control zone until Ti f that the vehicle exits the control zone, we impose some speed limits for the vehicle. Then we address the real safety constraint, where essentially for each vehicle I, we demand that the distance from the preceding vehicle K should be always greater than equal to some sort of distance delta I, safe distance delta I, which by the way is also a function of the speed of the vehicle, since the higher the speed, the longer the distance that we need to maintain from the other vehicles. And finally, we impose the lateral safety constraint, where essentially the vehicle I should have at least a distance delta from the vehicle crossing vertically the intersection. With this in mind, we can formulate our optimal control problem, which is minimizing the L2 norm of the control input from the time Ti naught that the vehicle enters the control zone until the time Ti f that the vehicle exits the control zone. Now, somebody might again argue, hey, how in the world this is an energy optimization problem, since you optimize the L2 norm of the control input, which doesn't have any energy units, right? Now, if you remember from the first part of the talk, when we minimize transient engine operation, we minimize fuel consumption. So essentially, this is what we're trying to do here. We minimize the L2 norm of acceleration, deceleration, minimize transient engine operation. And if you do that, you get benefits in fuel consumption. Now, to solve this problem, you formulate a Hamiltonian analysis by adjoining the Lagrange multipliers with all the inequality constraints. Yes.
So this process seems like a centralized way. You have access to all these vehicles, vicinity, and you can control that. But in reality, it's like distributed.
So actually, this is not centralized, it's decentralized. So each vehicle solves this problem at its own. So this vehicle, every vehicle I solve this problem and derive this optimal control policy on its own. Doesn't have any centralized supervision. They have only access to some information available to all the vehicles through a coordinator. So every time that the vehicle enters the control zone, the vehicle knows the existing information about the vehicles and solve the problem. But the solution is derived by each vehicle directly.
Oh, I see.
Now, if none of the state control or safety constraints become active, then you have a nice closed form analytical solution, right? That you can see here. However, if any of the state control constraints become active, then things are getting complicated. Let me just give you the flavor. I'm going to move a little bit faster here. So this is the case that none of the constraints become active. So you have a very nice closed form analytical solution. However, if any of the state control or safety constraints become active, then you need to piece the unconstrained and constrained up together, which come up with a set of algebraic nonlinear equations that you have to solve simultaneously to compute the junction points and also satisfy the Euler Lagrange equation, which means that you can no longer have a closed form analytical solution. You seek for numerical solutions like steepest descent and so forth and so on, which means that you cannot really implement this in real time. And even if you get the solution, you might essentially hit another constraint down the road. So you have to repeat this process. Just to give you another layer of details about the complexity of that, let's consider that we have the re-end safety constraint, and this becomes active. If this becomes active, then we impose some non-discontinuities in the influence function of the Hamiltonian analysis. And to address these discontinuities, we need to adjoin the Lagrange multiplier with a partial derivative of the re-end constraint with respect to the state, and adjoin this to the influence functions. And then we end up with a set of algebraic equations that looks like that, which is essentially can be solved only by numerical methods. So anyhow, to address this issue, the idea is how we can come up with a solution that can never activate any of the state control or safety constraints. So to address this problem, we start with the optimal solution of the unconstrained case, right, which is a nice cubic polynomial. Now, if you observe this polynomial, you see that this is a real function polynomial, it's strictly increasing. Actually, this is how it looks like. And also it's differentiated, which means that there is a one-to-one function, so which means that we can find the inverse of this function. As a matter of fact, you can apply the Cardano's method and you can find the inverse function, which we call time trajectory of the vehicle. And the time trajectory gives you the time of the vehicle with respect to the distance, with the position. So if we have this time trajectory, and we assume that we have all the time trajectories of existing vehicles inside the control zone, right? So once the vehicle enters the control zone, the vehicle has access to all the existing time trajectories. Now, what the vehicle can do is to drive this time trajectory for its own to avoid intersecting any of these time trajectories. And if it does so, then it means this implies that we don't activate any of the state control constraints. Now, once you derive this optimal trajectory, what you do, you inverse back, and this is now the optimal solution of the low-level problem. So essentially, with this approach, you have shown both the upper level and the low-level approach. Without decentralizing the region, right? Now, I'm going to skip this details. Essentially, this is the mathematical interpretation of what I just told you. Eventually, we end up with a nice optimization problem where we can show eventually that this problem is convex and there's no duality tab, which you can use this information to solve it in real time. Let me show you some simulation results that we did. We apply this approach in different scenarios, intersections, merging ways, and corridors. So this is an experiment in our scale city with an intersection. Several vehicles approaching the control zone, they start deriving the optimal acceleration deceleration profile to cross the intersection without stop and go driving, as we will see. We also apply this to a corridor that included a roundabout, a merging roadway, and an intersection. So we have about 15 vehicles in this scenario. You can see how the vehicles navigate through these traffics without stop and go driving and without congestion. Of course, if you ask, what if we increase the number of vehicles, then of course at some point we will have congestion because we reach the maximum capacity of the road. So there's nothing you can do about it. Actually, there's two things that you can do about it. You can either increase the speed limit to rush through the vehicles through the scenarios, or increase the control zone. But in both cases, you have limitations. You can do that. We also apply this in our demo vehicle, the Audi at the University of Michigan MCD. The way that we did this experiment, perhaps you know, in MCD they have the augmented reality. So you can have the physical entity in the field, and then you can make, you can create virtual vehicles broadcasting with this vehicle, with a physical entity. So we use this scenario. So we have the Audi alone in the field, but the Audi broadcasting with virtual vehicles that you can see on the left of your screen with the black vehicles. In the top, we have the baseline scenario without connectivity automation. In the bottom, we have the scenario where it runs with our control algorithms. So you can see in the bottom that as the Audi approaches the ramp, it can broadcast with the virtual vehicles, the black vehicles, and get to the merging zone without stop and go driving. So it eliminates this stop and go. Although in the baseline scenario, there is this virtual vehicles that blocks the Audi. So essentially the Audi is sitting without doing nothing. So that's the kind of approach that you can use, and you get several benefits in terms of fuel consumption. To quantify the benefits, we did a chassis dyno test. This is again the scenario we put the Audi in a chassis dyno at the Bosch facilities, and then we drive the Audi through the virtual environment of the MCD. On the left, you can see the baseline scenario where we have no connectivity and automation. On the right, we have the scenario with connectivity and automation. So here's the Audi on the chassis dyno going through the scenario. You can see in the baseline scenario, we have stop and go driving, right? Because there's no connectivity. Although in the scenario with all the vehicles are CVs, we have eliminated the stop and go driving, and we can sort of mimic the free flow, right? And through this approach, you get benefits ranging from 30% all the way to 34% improvement in energy. Now, if you do the following experiment, check out the window, the sticker posted on your window or your car about the fuel economy estimates, and compare the estimates that you have for city driving and highway driving. If you compare this, the difference is ranging between these numbers, between 30, 15%, and 35%, depending on the car that you have. So by eliminating the stop and go driving, essentially we translate the city driving to a free flow driving, and we get these benefits. So just to synthesize what we've seen so far, we've seen the model-based control approaches, where you have a discrepancy between the model and the actual system. So we cannot really, with these approaches, guarantee high performance guarantees. We see that in the case of the model-based control, we have to develop a PI or PID controller to control the vehicles. If you use reinforcement learning techniques, you can really have, you may have implications in the robust operation of the vehicle. We see that in the car, in the edge calibration. If you apply directly reinforcement learning technique, the physical set might end up stalling the engine or create implications with the robust operation. On the other hand, if you use supervised learning approaches, you can really guarantee have performance and safety guarantees, just because by only using offline data, you need to augment this with some sort of adaptive control approaches, and we did that. We see that with fuel injector characteristic curve. So the idea is how we can combine both. And let me take a few more minutes to just give you the flavor of this approach. So let's consider that we have an actual CyberPhysical system. And for this CyberPhysical system, we have some sort of noise observation of the state, right? And we have also a model of this system. It can be any model. Now, the idea here is to establish an information state which depends on both actual CPS and the model CPS. And if we show that this information state, the evolution of this information state, does not depend on the control strategy, then we can use this information state to derive offline the control strategy using the model. However, since this information state includes some information from the actual CPS, this control strategy should be parameterized with respect to every realization of the actual of the state of the actual CPS. Now, if we implement this control approach now to our system, then as we collect data, we can start learning the information state. And eventually, the optimal control strategy that we derive offline, we can make it, it will become optimal for the actual CPS as well. Now, let me give you one more layer of details. Let's assume that we have an actual system with some unknown dynamics. So F hat is unknown to us. And this system, in this system, XT hat is the state of the system, UT is the control input, and WT is the disturbance. Or are random variables defined in appropriate probability space. And then we have also some noisy observation of the system of the state, where Z is another random variable defined in appropriate probability state, space. Now, this is the actual CPS, and the problem here is to derive an optimal control strategy to minimize a total, an expected total cost criterion, right? However, to solve this problem is infeasible, just because we don't have the actual dynamics of the system. So, and what typically we do here is we have a model of the system, right? Simple model. We derive the optimal control strategy, and then we implement to the real system with the known implications about the discrepancy and performance guarantees. Now, what we want to do in this approach is we attach into our actual CPS the CPS model. We run essentially the CPS model in parallel with the actual CPS. And we establish an information state, which is some statistics. It's a conditional joint probability distribution of the state of the model and the state of the system, given all the history of the model. Now, if we can show that the evolution of this information state does not depend on the control strategy, then we can use this information state to derive the optimal control strategy by using the model. However, the information state has some information about the state of the actual system, which is not known to us, because this is an offline process, right? So when we eventually solve this problem, the control strategy will be parameterized with respect to every realization of my control of the state of my actual system. Now, once I start implementing this control strategy to both actual CPS and the model, and I run this, I start collecting data and I'm learning the information state online. Once the information state becomes known, then the control strategy that I derive offline becomes also optimal for the actual CPS. In the first result, what I'm showing here is, I'm gonna just run a little bit more because I'm running out of time. In the first result, we just show that this information state is a valid information state and its evolution does not depend on the control strategy, right? Once we establish this result, then eventually, this is the initial problem that we are addressing of the actual CPS. We reformulate this problem by attaching an error between the realization of the actual of the system of the state of the actual system and the state of the model. We penalize that. And we solve this problem offline using the model. We derive local control strategy, and this control strategy is parameterized for every different realization of the state of the actual CPS. And we can show eventually that this control strategy that we derive offline is optimal for the actual CPS. Just to give you some intuition about this, imagine that we solve this problem offline, and we have for every realization of the information state, a vector of control inputs corresponding to different realization of my actual state of my system. Now, as I start learning the information state, I will just select those control actions that eventually make my model to match the actual system. And once this becomes, then eventually the cost, the optimal control strategy corresponds to the cost of the actual CPS. And this is how you get to the desired result. Eventually, we hope that this approach can address problems, cyber-physical systems, problems cyber-physical systems will have a massive amount of data that can derive in real time and not altogether in advance. So by combining learning and control approaches, we can address some of the issues that I tried to outline in the first part of the talk when I showcase some of these challenges. So with this, I would like to thank you for your attention. I'd be happy to take any questions.
Pleasure. Go ahead.
Very nice talk. So I have a question about the real implementation of this approach, practical. So if you want to have all the inputs result, I assume you are doing some VGX with some infrastructure to support.
Yeah.
But what if some vehicles are improved and they don't have any device to provide? Well, that be a problem to attack your approach.
Yes. So what you see, we assume that all the vehicles are connected automated.
Yes.
You have 100% penetration.
Yes.
This is the solution. Now, for the case that we start deviating from the full penetration of CVs, we apply different approaches. This approach is no longer valid. You have to incorporate, some heuristics for this. But the way that we approach, we have two different ways to approach this. First, we try to use the CAD and learn from the human vehicle how it behaves, and then account this into our control, or use the CADs to form platoons of vehicles, and then control the entire platoon. Imagine platoons of vehicles, of human vehicles led by a CAD. So if you start controlling the CAD, you can start forming platoons, and then you can control all the platoons altogether.
I have a question about offline action. So it's usually they are doing like offline learning to learn a model on dynamic, and they do online policy to output the control signal. But why it's offline control?
Yeah.
So how does the offline control interacts with the environment?
That's a great question. So you use the offline, since you can have a full understanding of what you do in the controls, and you have all the techniques that you can develop optimal control strategies offline. We use these techniques, but since we don't have the information of the real system, we parameterize the strategy with respect to different realizations of the potential unknown parameters of. And then once we put this in action, as we start collecting data and we learn what is missing, then this strategy becomes optimal for the actual system. That's the idea. Now, that's a pure theoretical framework, and we are in the process to apply to some simple examples just to get a little bit more better understanding of that, and eventually apply to some real applications.
Okay.
We haven't identified the limitations of this approach yet.
And when you collect the data for the online learning, what kind of strategy or what kind of policy are you using to collect the data?
So eventually we just make observations of the system. All the past observations and control actions, the outputs. And then we condition this to our prediction of the next state. And then we learn essentially this statistic. We call this information state. So we essentially learn some statistics about and when this is our reference point to do the controls. So this information state becomes the state, the reference point for us to select the control action.
Okay. Thank you.
I have a question. You have a great journey from engine control to emerging mobility systems, and you have done a lot of work for engine control. They have improved the energy consumption, the efficiency, and so on. And now we are transitioning to electrical mobility and to alternative fuels. And I'm asking myself if it was to do this work again for electromobility and alternative fuels and see if we can do better, or what do you think? What is the next big step which we should address?
Yeah, that's a good question, Dr. Sam. So, unfortunately, I'm afraid that we might have to repeat the process since the battery is now the big unknown. Although before we try to optimize internal combustion engines, we try to add enabling technologies to improve the efficiency of the engines and try to understand how the engine operates. Now we have to do the same thing to understand the battery and how the battery operates. You see, you have an electric vehicle and you operate it in the cold weather, and right away you miss 20 to 40% of range right away, just because you now have different temperatures. And if you drive it in a different way, and then again, the estimated range will start changing, right? So we need to understand again, and the battery is much more complicated. Although with the engine, we have a basic, field that you can explore. With a battery, different technologies, you can have different behaviors, and then you have also the efficiency of the motor. It's a combination. So it's the way you operate the motor. It also have their own efficiency maps, the way that you operate the battery, and the way you operate your generator. So there's a big cycle of losses that you can have. But we already know that if you operate even your electric vehicle in a constant speed, low constant speed, that's the most efficient way. So there are some trends that are similar, but of course you can't really, for example, the approach that I have for the L to norm of the control input is if we consider electric vehicles, is no longer valid. Because I assume that if I minimize acceleration, deceleration, I have indirect benefits in fuel consumption. That's not the same argument that I can do for electric cars. I don't know. For example, it's better for electric cars to have sharp braking because you take free energy back to your battery, right? Yes, regeneration. But you can't really claim the same for the engine.
Yes, yeah, this is a great talk, also I like the way you presented it. Sounds like those are videos, with all these cars working on the US maps, and then you are talking, this is very nice. I do have one question, when you talk this optimization problem, do you assume this communication with your communication, right? So you assume this communication is stable?
Right, that's a great question. Yes, as control theorists, we like to make assumptions.
Yes.
So we assume no error, no delays, perfect communication, nothing wrong about this. Okay. That's the basic assumption. But in practice, none of that holds. You know, we see that. Actually, we see when we do experiments in scale city. You can see that this falls apart.
Right.
But, you know, and this is an open question, how we can address. Essentially, we transform everything to a stochastic problem, stochastic control problem. When you have uncertainty, this is your disturbance, this is unknown. And then you can use different techniques to, but they come with a cost of computational cost. Okay. So there's a trade-off. I mean, once you get closer to the reality, you have tools to address this problem, but you might not be able to implement this on board the vehicle. The whole idea of what I've shown is how we can practically implement that, you know, in a vehicle. So yeah.
Okay. Good. Thank you. Any other questions? They are all your own students.
Maybe one last question.
Yes, go ahead.
For the
Go ahead.
internal combustion engine, because I got my bachelor's degree on automotive theory and combustion engine. So do you think is there any much space for internal combustion engine to improve the efficiency from the perspective of engine itself? It's not from the multi-agents system.
I think we have exhausted this area. I think, and especially Wayne State University as Professor, I think, what was his name? Wayne State University.
Oh, Henning,
Henning,
oh, that's one of the.
and so many groups, they have done reads from Wisconsin University and others from Michigan. I think, I mean, let's assume, because all OEMs are about to retire internal combustion engines, I mean, conventional vehicles. By after 2035, there will be no selling, no vehicles available to buy with conventional.
Reach the state.
Yeah. So, but even if we assume that that was not the case, I don't really think that there is anything else we can do to squeeze any more percentage of efficiency. Connectivity was the next thing.
Yeah. Thank you. Thank you.
Now you feel much better, right? He got his bachelor in automotive engineer, then master in electrical vehicle.
That's
Now
it.
he's now doing PhD with me on autonomous vehicle.
That's it. You got all the spectrum.
That's the truth.
You got all the spectrum. You got it in
He knows all this, stuff.
You got it in good shape.
Oh, okay, I think we're done, right? All right, thank you so much. Okay, I will just say hi to.